Alright, this video is going to be about the WS2812. It's better known as the NEOPIXEL from Adafruit. It's a serial controlled LED with 3 LEDs, a red, blue, and green. It's getting real popular. There's a couple versions of this. This is the first version that came out. Now there's a version that looks like a regular LED with a frosted lens on it. I think it pretty much works the same way as this one. This one, of course, is the chip-mounted, surface mount chip version of the part. And reading the Chinglish here is pretty fun. First thing he says, control circuit and RGB chip are integrated in a package of 5,050 components. Well, that's a lot of components to put in this little guy. But what this means is, I'm pretty sure this is referring to the logic chip inside, and it's the 5050. Form a complete control of pixel point. So it controls your LED. Built-in signal reshaping, that's for sending data on to the next driver. So you can just connect these in a string. Built-in electric reset and power on reset. I guess the electric reset is the reset you send via holding the line low for a certain period of time, and power on reset make sure the chip's reset and ready to go when you power on. 3 primary colors, 256 brightness levels. That's 16.7 million colors, and can scan the frequency and not less than 400 Hertz. I'm not sure what this is referring to. I don't know if they're talking about how long it takes to send 16 million colors. I think 400 Hertz is a little optimistic, so I'm not sure what this means. Cascading port transmission signal by a single line. It's serial communications from chip to chip. Any 2-point distance more than 5-meter transmission signal without any increased circuit. I think this is saying it can transmit from one LED to the next over a 5-meter line. I think that's a little optimistic. I certainly haven't tested that. When the refresh rate is 30 frames per second, low speed mode, blah blah, not less than 12 points, high speed mode, not less than 1,024 points. At 30 frames per second, it's possible, following the spec, to actually transmit a little bit more than 124 LEDs. So I think with the processor and the overhead and processing signals, it's 1,024 points is probably doable. Data speeds 800 kilobits per second. Actually, by the timing spec, is a little bit faster than this. The color of the light were highly consistent, cost-effective. Cost-effective light. I like that. Okay. Applications. You got applications. We got answers. General description. The only thing here, they say also include precision internal oscillator and 12-volt voltage programmable constant current control part. I've not run into anything of 12 volts on this, so I don't know what's going on here. Data transfer protocol, use single NZR communication mode. Now, I've never heard of NZR. I've heard of NRZ. Typically that's what RS-232 uses, and it transmit plus and minus 12 volts, or plus and minus, actually it's from the spec is from 3 to 15 volts plus and minus. This communication protocol is definitely not NRZ either. And I don't know what NZR is supposed to be. It actually uses PWM, pulse width modulation, to send data. We'll be looking at that in the video, a little bit later on. And then the next thing, well, I guess that's it for the hilarity on this page. Here's a chip outline. It's like a DFN 6 pin. Here's the pin out. This is correct. The electrical characteristics, they specify 6 to 7 volts. I wonder if this there's a voltage doubler in that 5050 that makes it 12 volts. I'm not sure what's going on there. Everything I've seen is 5 volts, runs great on 5 volts. You'll see in the video I'm just running the processor and the LEDs on 5 volts and plenty bright. Works fine. Input voltage spec here actually contradicts a little bit what their spec down here. Input current is 1 microamp. Voltage input high 3.5 volts minimum, and voltage input low 1.5 volts minimum maximum. So any microprocessor you care to pick can meet this no problem. Here's your switching characteristics. Duty ratio 400 kilobits per second. I'm not sure, and what this is like half the bits per second. I'm not sure what they're just saying. Duty ratio 50%. 50% of 800K is 400K. Not really sure what they're trying to point out there. Here's the intensity data. You see that green is the brightest. Red's about half as bright as green. Blue's about half as bright as red. I've seen that. We'll look at this in the second video on color mixing. But I really haven't noticed that blue and red are off that much, but the green is pretty obviously brighter than any of them. Seems like blue is the dimmest, and red's not too far from green. But we'll save that for later. Here's the timing chart. We'll be going through this in the video in a lot more detail and a lot more meaningfully. Here's the scheme for sending data out of the processor and into the first LED. This is for a chain of 3 LEDs. It first sends 24 bits, then the second 24 bits for the second LED, and 24 bits for the third LED. You have the 50 microsecond reset, which actually loads this data into the chip's PWM, and the LEDs light up. And then that cycle just repeats. You can change the data if you want, whatever, for the next pass. So data coming out of the first LED and going into the second LED looks like this. As soon as he receives his 24 bits, he starts sending all the bits that come following. So the second LED starts receiving his 24 bits, and the third LED's data is also passed in. You have the reset, and that continues. Now data coming out of the second LED and into the third LED looks like this. It's just the third LED's data. Second LED collects his 24 bits, and as soon as he does, he starts sending whatever follows, and that's the third LED's data. You have the reset, and that happens over and over again. Data coming out of the third LED, data never comes out of the third LED because that's all we send. The sequence is the data of the 24-bit data is green. Most significant bit is first to the green least significant bit, then red most significant to least significant, and then the blue most significant to blue's least significant bit. And typical application shows 3 chained together. The micro sends data in. Each one passes data to the next LED and to the next LED. VCC is shown with the filtering, and I'm pretty sure VCC is for the logic chip. VDD is going to be for the LEDs. And I don't know if you can see here, but the power connections are labeled as 5 volts. So I don't know what the 6 to 7 volt stuff was we saw earlier. But that's basically what we need to know to run this thing. I've got one more thing I want to look at real quick, and that's on this data sheet, which is the WS2812, which is the chip. This is basically the chip with the 50/50 part in it. And he says that output voltage is 12 volts. So somewhere there's an application or a way to get 12 volts operating on this. I don't know what it is. You can just ignore this, and it hasn't ever affected me, and I haven't ever noticed anything out of the ordinary with 12 volts. But anyhow, that's basically what we need to know to drive this guy. And now let's take a quick look at the code I'm using to drive our test frame. Okay, let's take a look at the code here because it's kind of unconventional. What I'm doing is setting the port output, waning a no-op, 1 or 2 no-ops, and then clearing the port output. So that gives us our high and low for 1 bit time. Now 0 is going to be set the port high, wait 1 instruction, clear the port, and wait 2 more instructions to make a full bit time composed of 5 instruction cycles. Then for a 1, you set the port, wait 2 no-ops before clearing the port, and wait 1 no-op to make our 5 instruction cycle bit time again. And it just keeps going like that linearly. And the reason I did this is because there's no computation time figuring out what bit to send, figuring out which LED we're on, which data bit we're doing, which color we're doing. And it does that for 1 port, and it does it for the second LED that I have on the board. And it's just like that. So there can be no timing problems introduced by just driving the code this way. And the reason I did that is just to make the tests to be able to tell where my anomalies are coming from. And I insert to alter the timing. I call this delay routine, which here I pick one of these. Most of them are commented out. I pick one data bit to load into delay control low, and then this delay routine runs, and I get all these several delays, and I can tell by putting the delay in when I affect the color on the LED. If it starts flickering, if the color doesn't show up at all, if the board resets. This just makes a controlled way to introduce the proper delay and to search for the limits on how long you can wait before you get to the second bit, and how long the reset needs to be. Now all this will become more clear in the video. So let's go ahead and go to that part of the video where we insert these delays and see what happens to the chip. Okay, here's the basic setup we're going to be using for our WS2812s. We got our pick and two of the WS2812s mounted on breakout boards, so I can plug them into the breadboard. I've got an extra one we're going to be playing with too, so it's just on a. I can show you here. It's just on a little breakout board like that. So I'm kind of disappointed in the ability of this camera to focus on things up close. I'm pretty much dismayed at the focusing ability of any camera I've seen on YouTube or my camera or anything. This autofocus is a joke. but it's what we're stuck with. So here I'm trying to get a close-up shot of the three LEDs lit up at their minimum brightness. It's not going to quite do it. You can see the chip, the little dark spot just left of center, and the three LEDs are on the right, but they're just not gonna quite show up. I don't think my shutter button does anything, and well, that might be a little better, but the individual LEDs are just, it's just not going to focus with the brightness contrast. That's the best I can get. So now let's look at some of the tests of the signal and some of the electrical characteristics of this chip. Okay, so here we are, the waveform for pumping out our minimum green and minimum blue. So we're sending green to the first LED, we're sending blue to the second LED. Now here's the basic thing we're sending. We send the three colors. This is the data going into the first LED. This is the data coming out of the first LED and going into the second LED. So we can see the full string goes to the first LED. After the first LED fills up, it's 3 bytes. Then it starts sending everything else that comes out to the next LED. So we're sending green. Minimum green should be in this first data string. So if I turn the right knob, the correct knob, expand this out. So our first 8 bits are green. 1, 2, 3, 4, 5, 6, 7, 8. And you can see the pulse width is greater for the 8th bit. That's green bit 0, so it's the minimum green is on. Now let's look at some of our timing here. And if I would quit turning the voltage adjust. So here's for a 0. We're on 200 nanoseconds per division. So that's about 500 nanoseconds for the high. Here I've got my cheat sheet. 500 nanoseconds for a high. We're right on the edge of this timing diagram. Normal is 350 nanoseconds. 500 nanoseconds is your max, and I'm right on it, running at 16 megahertz on this pick. So I've got 250 nanosecond cycles, so 500 is as close as I can get, so I'm right on the edge. Then for the low time, that leaves me with 800 nanoseconds, and I believe two, 4, 6, almost 800 nanoseconds. So 750 nanoseconds. So we're just right before there. So we're good on the low period. We're right on the margin on the high period. And that's for a 0. I'll scroll over to our 1. Two, 4, 6, 750 nanoseconds. For a 1, we're good. We're real good there. 700 nanoseconds is nominal. We got up to 850 nanoseconds. So we've got a lot of margin on that. And for the load time, we're 600 nanoseconds. 500 nanoseconds. And we're good by 50 nanoseconds, 450 nanoseconds. Is the margin there, the minimum there. So we're good by 50 nanoseconds there. So really, we're really pushing our luck on sending to 0. But so anyway, that's what you saw, the green LED first, and that's in the 8th bit we transmitted of the first byte. Now if we go and look at blue on LED 2, which is the last byte, and we look at the last bit, we should see a 1. We should see the 1 bit here. Whoops. I got to quit moving my voltage reference. And here we can count backwards. 1, 2, 3, 4, 5, 6, 7, 8. There's the 8th bit starts. The blue starts there, and there's the bit 8. Setting it to 1, and we have green and blue. And what that looks like under LEDs, I don't know if this will photograph. There's our green and blue. Green first, blue second. Okay, here we're going to take a look at the reset time in between setting our groups of data. We're on, we got a sweep speed here of 5 microseconds. So we're 5, 10, 15, 20, 25, about 27, 28 microseconds roughly. That's about half of the 50 microseconds that's specified as the reset time. So I guess the big reset time ensures that everybody gets reset. We're at half that, and it's still resetting correctly, or loading this blanking period loads the new data into the LEDs, and so at half of the spec we're still loading the LEDs correctly with no problems. So let's take a look at a little shorter period. Okay, now I've changed my time, my sweep speed to 2 microseconds per division. So here one transmission ends. We've got 2, 4, 6, 8, 10, and 11 microseconds, and the LEDs still look great, no problem at all. So that's 20% reduction in the spec, and the LEDs are getting reloaded. So let's drop it a little more and see what happens. Okay, so my camera's going in and out of focus here. I don't know what the hell's wrong with it. I've got anyway, I've stepped down to what am I on? 1 microsecond per division. You can see the cycle ends right here. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9.8 microseconds to the next cycle. The LEDs are still behaving fine. That step from 11 microseconds, that's the resolution that I can step down to. This camera is just, golly. I hate these digital cameras focus. If they're going to do it, why don't they do it right? I mean, they can go in focus, obviously, but then they drift out. Most annoying thing I've ever seen. Wish I had focus rings on these things. Okay, well, let's drop down a step and quit complaining about cameras. So here is 9 microseconds. 1, 2, 3, 4, 5, 6, 7, 8, 9 microseconds. And the second LED is blinking. So is losing some data. I don't know if you can. I've got a combination now of colors so this test shows up a little better, and it looks like it's going to filter out. You can see the blue, mainly blue. You can see them changing colors from time to time. So 9 microseconds are right on the edge of it failing. So let's back up one and see if we get more stable. Okay, now we've stepped down slower, and the LEDs look pretty steady. Run 1 millisecond again. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 9.6, something like that. And it seems our LEDs are doing pretty well. No obvious flickering. Why don't you focus? Anyhow, that looks pretty stable at about 9.6 microseconds. Okay, here we place the delay, and it's about 8 microseconds, I think. We place it after it's 16 bits. We place it right after the end of the red, and when it should start doing the blue. And we see it's caused a weird problem. The LEDs are kind of blinking. I'll show you those in a minute. But it also is chopped off. It's truncated when the bits that are on coming out of the part. So it seems to only be doing the last 8 bits or so. So anyway, this period is 1, 2, 3, 4, 5, 6, 7, 8, and 8.2 microseconds. And it has caused, see how many bits are showing up here. 1, 2, 3, 4, 5, 6, 7, 8. Just looks like the 8 bits. It's caused its output rate to reset before it starts sending data again. So that's a pretty unusual effect there. So at 8.2, so we need to, that's too long a delay. So we'll have to decrease that and see what we get. It looks like the LEDs have actually warmed up to it and they're not flashing too much anymore. Oh well, we'll check those later when there's actually something to look at. Okay, now we've slowed the delay down a little bit, so it's a little bit less. We've made some improvement. I'm getting 16 bits out for the, or wait, maybe that is, let me take a closer look, see how many bits that actually is. Okay, it's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 4. Yeah. They're all there. Okay, they're all coming through. And our delay is going to be about 8 microseconds. 1, 2, 3, 4, 5, 6, 7, and 7.4. About 7.4 microseconds. And the LEDs are acting weird. I need to reset mine. Maybe you'll see the red flashing a little bit. So that's not stable either. So we have to make that delay a little bit less again. Okay, I've slowed it down one more step. We're getting all our bits. The LEDs look real steady. And let's see what this is. This delay. Is going to be 1, 2, 3, 4, 5, 6. That's 6.8 microseconds. So that's how long a low, while you're still writing good data, that's probably the maximum you can get away with for generating, having your line remain low before it'll actually reset. So that tells you got a little bit more programming time than what the spec says. And if we take a look at the LEDs, you can see maybe they're pretty steady. I haven't seen them flicker at all. Don't take this thing going in and out of focus just as a flicker, but that looks pretty solid. We can probably shoot for that. So when you're generating code, that'd be the max. You'd want to spend, you know, changing. You have to calculate your data, get a new bit loaded, send it out, come back, calculate your data. You also need to turn around between bytes and the turnaround between LEDs. So that gives you 6.8 microseconds. At 250 nanoseconds, that's going to be 24 and a half, 24 to 5 to 6, 26 instructions to get done before you get ready for your next bit. We might put in a 20 megahertz crystal and maybe do some more timing or see what we can get away with. And but now I think it's time just to look at color, looking at some color values and seeing if we can generate whites and intensities and things like that. We'll do that next.